Thank you very much. Thank you very much for the invitation to give this talk here, and thanks everyone for coming. It's really great to see such a nice audience. Always makes me happy to see a room filled up, a diverse room. So I was asked to give an hour-long talk and just learned that we have 90 minutes. So that means you can ask tons of questions. So don't hesitate to ask if anything is unclear. I was also asked to give a colloquium talk. And so just a few words, I know that this audience is very diverse in many different senses. In particular, we have undergrads and advanced graduate students and postdocs here. So since this is a colloquium talk, I really encourage all the undergrads to stick with it, try to listen until the end. So for such talks, it might happen that you get lost at some point, and then you keep listening, and then you understand things again. So it's not a talk where each slide builds up on the previous one, but you will be able to understand future slides, even if you miss the previous slide. For the advanced grad students, this means the first few slides might be super boring for you. So there are two options. You can either sleep and manage to wake up on time, or the other option is you will likely in your life have to give a colloquium talk yourself sooner or later, in particular when you give job talks. So the other thing you can do is just listen to it and think about how would you give a colloquium talk if you were supposed to give a colloquium talk? What do you think works well in my talk? What do you think doesn't work well? And how can you give a better talk than I give it? And you can also tell me afterwards, so I know how to give it. All right, so that's enough about pre-stuff. Now I want to tell you about representations of P-adic groups. And so this is very much related to actually the two talks series we see, in particular Charlotte's talk series, but also Anna's talk series. Charlotte's more obvious than Anna's. We learned in Charlotte's talk already what representations of groups are. So the key thing we need to understand, what is this P-adic group? So I want to tell you what does P-adic mean? So what is P? P is prime number. Choose your favorite prime number. And then we can define a P-adic absolute value as follows. We take an integer, write it as P to the S times R, with R and P co-prime. And then the P-adic absolute value of that integer is 1 divided by P to the raised to the S power. So that means the P-adic absolute value measures how often an integer is divisible by P. If an integer is very often divisible by P, then the P-adic absolute value is tiny. And so this allows us now to define what the P-adic integers are. So the official definition says that P-adic integers, which is denoted by Z sub P, ZP, is the completion of the integers, as you know them, by this new absolute value, this P-adic absolute value. And so that means that a P-adic integer is just of this form here. You can write it as A0 plus A1 times P plus A2 times P squared and so on, where these coefficients A0, A1, and so on are some integers between 0 and P minus 1. And this, well, if you stop it anywhere here, if we stop here and just calculate, add these numbers up, we get an integer, but we can go on to infinity because this will converge because higher powers of P have smaller P-adic absolute value. So that means the new thing that we're adding to the integers is that we allow the exponent here to go into infinity and keep going. And then we can define the P-adic numbers in two ways. We can say either it's just the fraction field of the P-adic integers, and we write it as QP, or as the notation indicates, we can also start with the rational numbers Q and complete those with respect to the P-adic absolute value. So that's the formal definition. Maybe it's a bit confusing if you see it the first time, like how does this object look like? So I want to give you an example. So here are the three-adic integers. Here's a picture how they look like. I said they are power series in 3. And so let's see, what is it? So we could just look just at A0. A0 can be either 0, 1, or 2. And the distance between, say, 0 and 1 is just 1, because the difference is not divisible by 3. So the P-adic absolute value is 1/3 to the 0, so that's 1. It's getting more interesting when we add a second digit. So let's add a second digit. So this number here, it's 1 plus 0 times 3, so that's just 1. While this 1, 1 stands for 1 plus 3 times, plus 1 times 3, so 1 plus 3 is 4. And so the difference between 1 and 4 is once divisible by 3. So the P-adic absolute value of the difference, that's 1/3. So that means if two of these power series have the first digit the same and only the second differ, then the difference is 1/3. And that means we get these smaller triangles, it's here shown as triangles, which means that all these integers here, that's 1, that's 4, and that's, I can't, 7. All these 3 have distance 1/3 from each other, but anything in this triangle has distance 1 from 0, for example, or also from 3 or from 6, because the difference is not divisible by 2. That was the second step. Now we can keep going. We can play that again and add a third digit, wherever you like to add a third digit, and then you see the difference here will be 1/3 to the second power, so 1/3 squared, so 1/9. And you get all these smaller triangles. But again, everything in here has distance 1 from everything in here. And now you can keep going, but I can't draw this anymore. And you can imagine what happens. You just get a fractal. So that's what the p-adic integers look like. They look like a fractal. So even though they arise as a completion of Z, the integers, it looks very different than the real numbers. And I want to contrast these two now. So the real numbers, you all hopefully remember that these are just the completions of the rational numbers by the regular absolute value. And I introduced this weird p-adic absolute value that gave us then the p-adic numbers. And the real numbers are this line. Usually when you draw it, it's a line. Well, the p-adic numbers, I hope I convinced you, it's this frac. And so even though they arise in a very similar way, they're very different. The real numbers, they are connected. It's just a line. Well, these p-adic numbers, they are totally disconnected. You can see that in the picture very well. And here's another crucial difference that takes a moment to realize. So the real numbers, they have only one compact subgroup under addition, which is the trivial one. Because as soon as some real number, say 5, is in your subgroup, then 10, 5 plus 5 has to be in your subgroup, 15 has to be in your subgroup, 20, 25, and so on. So it will never be compact. On the other hand, for these p-adic numbers, there are infinitely many compact subgroups under addition. So for example, ZP, this picture here that we've seen before, that's compact. It fits in this ball here. It's something compact. It doesn't go up to infinity. The same with P times ZP. So that's the smaller thing here. That's closed under addition. It's a subgroup. And it's also something compact. The same with P squared times ZP is also compact. Or P to the 15th times ZP, or 1/P times ZP. So there are tons of compact open subgroups. There are infinitely many, and they even form a basis of neighborhoods of the identity, because they're getting smaller and smaller and smaller. So they form a basis of open neighborhoods of the identity. So that means it's very different from the real numbers. And these compact open subgroups, they play an important role in the representation theory that we'll soon encounter. So now the next question is, I said, well, these are the p-adic numbers. And I said, well, oh, it's gonna guess. On my title slide, I want to study p-adic groups. So what are p-adic groups? So first I would like to remind you there are some objects called real Lie groups. So for colloquium talks, you usually assume that people have some basic understandings of what's at the level of qualifying exams. If you're an undergrad, you might not have encountered necessarily Lie groups yet. So what you really should think of is GLN over R, so the n by n matrices that are invertible over the real numbers. That's a real Lie group. But you can also build nice subgroups of that. So really the groups I want to look at are nice subgroups inside GLN of R. So for example, the group SLN, all the matrices of determinant 1, that's a nice subgroup. Subgroups that come from nice equations. Two other examples are SON. I've written the formula over there. So these are just all the matrices determinant 1 that satisfy this very explicit formula that the transpose of the matrix times the matrix is the identity matrix. Or another one is the symplectic group, which has a similar property, but instead of the identity matrix, you put in here a matrix that I call J like Jessica. Well, it's actually called J usually. Which has -1s on the lower antidiagonal and 1s on the upper. And that's called the symplectic group. It preserves the symplectic form, so this defines as a symplectic. And so that's what I mean by real Lie groups. It just mean groups of this shape, nice subgroups of GLN. And so what are now p-adic groups? Well, just do the same and replace the real numbers by the p-adic numbers. So over there I already wrote K for the field rather than actually specifying if I mean the real or p-adic numbers. So you see all these formulas on the side, they work also for the p-adic numbers. We can just look at invertible matrices over QP. or those of determinant 1, or those that preserve an inner product, that's the first example, or those that preserve a symplectic form, the second example. And that's what I mean by P-adic group. For the dots here, so for those who are more familiar with real Lie groups, there are also these exceptional groups. There's a classification by Dinkin diagrams that tell us something about these groups, and the same thing works for P-adic groups. So you are also welcome to think of the most craziest example you can come up with, something like E8 or so, for people who have heard these words before. So there are funny names like E6, E7, E8, G2, F4. So there are some exceptional groups, but they are all also nice closed subgroups inside GLN. It's just that the formulas to describe them are more complicated, so I can't just write it that easily. So that's the P-adic groups you want to study. I want to introduce a sister field to that. So first, let me recall what the P-adic numbers are. So I said earlier integers are power series, and I said that the P-adic numbers were the fraction field, or you complete Q. And in terms of this expression, it just means you allow finitely many negative exponents here. So you allow to go to a minus n times p to the minus n, where a minus n is, again, something between 0 and p minus 1. And so a first question, if you learn about the P-adic numbers, that you might wonder is, what is the characteristic of this field? And the answer is the characteristic is 0. Well, what can the characteristic be? It's some integers and prime number that is 0 in our field, but I think the canonical guesses here are either 0 or p, and p itself appears here as a non-zero number. So the characteristic is not p. P is different from 0. And also all the other integers, the other prime numbers that you can come up with, they are non-zero in here. So the characteristic is indeed 0. None of the prime numbers is 0 inside this field. But there's a close friend to that, and that's what I call the Laurent series over a finite field with p elements. And that looks essentially the same. The difference is just instead of p, I use now a dummy variable that I call t. So that means I take Laurent series, which means power series in t, where I allow finitely many negative exponents with t added to it. And what are the coefficients now? Again, the coefficients are numbers between 0 and p minus 1. In other words, I take them in the finite field with p elements so that I can add and multiply these. And it all makes sense. And they look very similar, and a lot of things work very similar for these two fields. The main difference is now the characteristic is actually p, because now p appears in this power series as an A0 here, and p inside this finite field with p elements is equal to 0. So that's the finite field with p elements, that is the field where p is the same as 0. So that's the main difference between these two fields, the characteristic. So if you haven't seen P-adic numbers before, you might choose to either think about these P-adic numbers or think about the Laurent series. Some people who come from analysis, they prefer Laurent series because they know them where the coefficients are complex numbers, and now you just replace the complex numbers by a finite field with p. And so when I talk about P-adic groups, I said before, take one of these groups and plug in the P-adic numbers. Now I also want to allow you to plug in the Laurent series over a finite field. So that's what I mean by a P-adic group, just one of these groups here. All right. Any questions so far?
Yeah. I guess given the fact we don't have a definition, which is why also makes me feeling a bit uncomfortable, because like you have your FP is a characteristic P, but QP is mixed characteristic.
Yeah.
So why are those folks allowed to be like P-adic group?
Why are they both P-adic groups? Because I like to abuse notation and call them P-adic groups rather than call them P-adic groups and groups over normal series over finite field with p elements. That's not a satisfying answer. It's some people call both P-adic groups, some call only the first one P-adic groups that really come from P-adic numbers. I just want to make my life easier.
Right.
If you want to have a really precise definition, just give it to you. I mean the F points of a reductive group where F is a non-Archimedean local field. So that would be the formal definition. Since this is a colloquium talk, I'm not going into these details, but rather say these are P-adic groups so that we all understand what's actually happening here. Yeah.
For the symplectic group over the P-adic numbers, does J change?
No, J is always this J. Excellent. Yes. Because this J makes sense over all fields. characteristic to it actually not the same as SO, but it's let me maybe not worry about the case where -1 is equal to 1. Excellent question. All right, I don't see more raised hands. These are the p-adic groups, and now I want to study the representations of these p-adic groups. So from now on, F will denote either QP or the Lorentz series over finite field. Or if you want to be fancy, a non-Archimedean local field, for those who have heard these words before, but it's really these fields that I'm considering. And G is a p-adic group, like one of these groups we have seen before. I just make my life easy by abbreviating these fields by N. And here's a definition of smooth representation that I want to consider. I start with the definition of a representation that Charlotte gave on the first day. We recall that we said that a representation was a group homomorphism from our group G into the space of automorphisms of a complex vector space V. So that's what we started this lecture series with. Charlotte introduced that. The interesting thing is for us, usually V is infinite dimensional. So we now work with infinite dimensional vector spaces while Charlotte worked with finite dimensional vector spaces usually. And since these are now infinite dimensional vector spaces and the groups themselves are infinite, like these groups GLN over the p-adic number, it's something infinite, I want a bit more structure. And I told you that there is this topology on the p-adic field. So we had the fractal that appeared, which also gives a topology to the group. And so I want to take this into consideration when defining smooth representation. So I call a representation smooth if, in addition, the last line here holds, I want that the stabilizer of every vector is open. So I take any vector I want and look at all the elements that fix this vector, and I want this to be open. So that means every vector is fixed by something large. It's fixed by one of these red triangles we saw earlier, but now at the group level. Sorry, not red triangle, red circles. So that means each vector is fixed by something large, but still the group is infinite. So still there are infinitely many elements that act non-trivially, and we get an infinite dimensional vector space usually. And that's actually a nice category that we can study. And here's the long-term goal. What we want to do is we want to understand the category of all these smooth representations. We want to understand all these smooth representations, the building blocks, and also how we can map between these representations. Map between these representations are just maps that preserve the action. And so how do we do this? We know that there are certain building blocks. They are called supercuspidal representations. So that's always a scary word. I don't know, maybe the super makes it scary. And the idea of this talk is that I want to explain what that is. And the short answer, it's just building blocks. So it's something very simple. And the first problem is we want to construct all these building blocks. Let me just move the long-term goal and the problem one up. And let me just say a bit, why do we want to do this? So when you give colloquium talks, it's always important to also motivate why do you do things, because people usually outside your area don't know why you care. I myself just care because it's cool to study these things. But it's also helpful to write down these representations very explicitly to do all kinds of things in the representation theory of p-adic groups. So what questions can you ask? You can, for example, ask, let's take a subgroup, let's restrict our representation to the subgroup. What happens? What representations occur? If you want to answer that question, well, you need to be able to write down these representations somehow. Otherwise, well, if you don't know what they are, you can't really say what happens when you restrict them. But there are also all kinds of interesting things like transfers of representations from one group to another. If you want to understand that, you also want to write down these representations as explicitly as possible. And also, who doesn't like to write down things explicitly? There are also applications if you want to write down an explicit local Langlands correspondence. So we see that a bit in Anna Karyani's talk, the idea of the Langlands correspondence. So the idea is that we start with the representations of a p-adic. So Anna Karyani talks about the global version more, we talk more about the local version. So that means we start with a representation of our p-adic group, and we want to attach to it something from number theory, something from the world of number theory, which is a Galois representation roughly. But if one wants to do this explicitly, well, you need to know how to write down the representations to start with in order to explicitly attach something in the other world to it. There are also applications to automorphic forms. These are generalization of modular forms, something we have seen in Anna's talk. So you might want to understand what are these automorphic forms, what are these modular forms, are there nice congruences between different things? well, refer here to a joint paper with Sarushin, in which we use results about these representations of p-adic groups to construct congruences between automorphic forms. So that then enters the global world that we see in Anna's lecture series. And well, the way it enters is through the adels, where we see that if we, in the global world, we look at all the p-adic numbers for all the p's together, and if we specialize to one p, then we are in this local group. There are also many more applications. I've heard about applications of mirror symmetry, conjectures, and so on. And I encourage you to just find more applications yourself. So here's the vague answer. We can do this. I will undermine assumptions. And for now, I want to assume that we can do this. And later in this talk, I will explain to you a bit more what I mean with we can do that. But for now, let's just assume we're done with that part. Let's assume we know all the supercuspidal representations. Let's black box this. Then, how do we get the rest out of that? Well, before doing more abstract things, let me give you a very explicit example. You might be crying already internally that you want to see a representation. So here's one, which is actually analogous to what we have seen in Charlotte Chan's talk already. So I take my group to the SO2 over the p-adic numbers, and inside there I denote by B, because it's often called Borel subgroup, for Borel, who used to be here, the upper triangular matrices inside this group SO2. So they have determinant 1 and upper triangle. We have seen the same over a finite field in Charlotte's talk. And now I need to give you a vector space first, and then I need to give you this action on it. So here's my vector space. I take all the functions from the group to the complex numbers that satisfy the following property. F of bg is equal to f of g for b, any element in my Borel subgroup, the upper triangle matrices, and any element g in the group. So that's just the first line. If I stop there, this is the same definition as we have seen for finite groups in Charlotte's talk, except, well, I write my b on this side and Charlotte wrote it on that side and had a character in there. So there's some difference in conventions. I just don't like to write inverses. And Charlotte seems to prefer to write inverses. If you write it on the other side, you have to write a bunch of inverses. But now, since we work with these p-adic groups that have this topology and all these fun things on it and no longer as a finite group, I want to take this into account and ask the function to be locally constant. So let me show you a bit more explicitly what this means in this setting. So this formula asking f of bg to be f of g can be also said by we just look at functions on the quotient g mod b. So all the functions where on b nothing new happens. And what is this quotient here? So the quotient between SO2 and B is essentially just whatever entry is here. If you actually sit down and do the exercise, you will find out it's actually whatever entry sits here, but divided by this entry here, which means, in other words, it's called P1 of QP. So the projective line over QP, which just means it's QP together with infinity. Infinity comes from the fact that if we take here a number and divide it by 0, we get infinity. So really this quotient is QP, which you have seen before, and infinity. And QP itself contains like ZP, which is this picture here. And now the function should be locally constant. So that means it should be constant in one of these circuits, like one of the very small circuits. That's where it needs to be constant. So that's what's locally constant. So it's something really explicit. You can sit down, write what it is, understand what it is. But still, it's something infinite dimensional because this is just CP and QP goes on to infinity. I've just not drawn this because it's fine at my slide. So that's the vector space. It's an infinite dimensional vector space, but it's something rather concrete. And now I need to give you the action. So I need to give you this map from G into the space of automorphisms of the vector space, which also satisfies this nice smoothness condition. What does it mean to give a map from G to the automorphism of the vector space? It means for every element G in my group, I need to give you a map from the vector space to itself. And here's the map. I take one function. I mean, that's how I write my function in here. And I send it to the same function, except I write translated by G. So that's my map. You've seen this in Charlotte's talk where they put G inverse on this side because she had the condition on the other side. So there are these two conventions that exist. And that's a smooth representation, so you can check the smoothness is satisfied, which just follows from the condition locally constant here. So that's why I put in the condition that it's locally. So here you go, you have seen your first example of a smooth representation of a p-adic group if you haven't seen these before. And it's very similar to what we've seen from finite groups. Now I want to generalize this and want to get from just this one example to a huge number of examples that are almost everything. And I do this via the notion of a parabolic subgroup. So parabolic subgroups already secretly showed up, but I don't think they were defined yet. So here's what a parabolic subgroup is. Let's do it for GLN. You can do it for all the other groups in the same way. It's just a subgroup of this shape. So what does it mean? You choose a number and sizes of blocks. So I've chosen 2 by 2, 1 by 1, 3 by 3. That was my choice. And now I take all the matrices that have any entries you like in the blocks and above the blocks and below the blocks. That's my parabolic subgroup. I can choose any block size I want and then take the block upper triangular matrices. To be very precise, instead of just choosing number and sizes of blocks, I should also choose an element small g in my p-adic group, so inside GLN, for example, and then conjugate that. So I fix my g and then take all the elements that is after conjugation by g or g inverse have this shape. After conjugation by g inverse, I cancel that. They have this shape. That's what a parabolic subgroup is. And why are these parabolic subgroups so important? Well, they have a really nice structure, and here it goes. It's called a Levy decomposition. It says that if you have our parabolic, I call it P for parabolic, that's upper triangular. I can write this as a semi-direct product of two things. I can take all the matrices that are block triangular, so zeros above and below the blocks. I call this M, and that's a Levy subgroup. That's the name for it, named after Levy. The nice thing about this M is this is again a really nice group. It's again a p-adic group. For example, here it's a product of GL2 times GL1 times GL3. So it's a really nice group. If you do it with symplectic and orthogonal group, it would be also a product of some GLNs and orthogonal symplectic groups. And so that means here we can already construct representations, and that's what we use in the model. And then there's this other thing here that's called U. It's called U for unipotent radical. That's just the name for it. These are unipotent matrices. What are unipotent matrices? Well, matrices of these shapes. So matrices of ones on the diagonal that are upper triangular. And in this case, they are block upper triangular. And I can write every matrix in here as such a product. And that then allows me to do something called parabolic induction. So I take a p-adic group, G, and take a parabolic subgroup as above. And now I take sigma representation of M, a smooth representation of M. So a map from M to the automorphism of an infinite dimensional, usually infinite dimensional vector space. Sometimes it's also finite dimensional. And then I form the parabolic induction. So here in gray, it's what we did before, and now it's the generalization here. So what is it? It's functions from G to this vector space. So previously we just had C, the one-dimensional vector space. Now it's this vector space of the representation that satisfy the following properties. We want that if I write f of m u g, where m is in m, u in u, and g is any element in g. It sounds weird to say m and m. So small m, capital M, small u, capital E, and so on. The property is that this m and u pulls out via this representation sigma. So that means it's sigma of m times f of g. Does this make sense? Let's see. So f of g is an element of the vector space. So this is an element of the vector space. And sigma of m, sigma is the map from m to the automorphism of the vector space. So that means really what it is this is an element of the vector space, and this is an automorphism of it. So it acts on this element of the vector space to give us a new element in the vector space. So that makes sense to write it that way. And this u just drops out. We forget about the u. And that's the same as before, where we just had sigma, the trivial representation, so the b just dropped out and nothing happens. Secretly, you can write here multiplication by 1 or the trivial action more precisely. And so that's the parabolic induction. That's the vector space. What is the action? The action is the same as before, just this right translation. And the notation that one uses often is also to write this as in from P to G of this representation and the space. I think that's what Charlotte also used together with her other notation that's more coming from the linguistic theory. And so this parabolic induction is a nice way to start with a representation of a smaller group and build a representation of a bigger group. So now you can create a lot of representations. Any questions at this point? Yes.
Is there an intuitive reason for why U drops out, or should we just forget about it?
Oh, that's an excellent question. Is there an intuitive reason? Yeah, because the representations of U are very different. It's an excellent question. I'm wondering how to best answer. So I said I want to talk about P-adic groups, and P-adic groups are really groups of this shape and not of that shape. Because the representation theory of groups of this group is very different. And so I'm really interested in the representation theory of groups of that style, and to take representation from that group and build new representations out of it.
Maybe one answer is that you don't have to, and that's remarkable that you can get them all without taking.
That's a good point, yeah. It's just remarkable that it works, was the comment. You would expect that you have to take this into consideration to get everything, and remarkably somehow you don't. That's some magic that happens there, yes. And so in particular, so maybe now I can say that I was asked earlier, what P-adic groups do I really mean? I said this word reductive groups, and reductive group just means that the unipotent radical is trivial. So the unipotent radical is the maximal connected normal subgroup of this shape. So that is conjugated to upper triangular matrices with ones on the diagonal. And the groups we consider are those where there is no normal subgroup of that shape. So that's why we quotient out to get again a nice P-adic. So that's how we can construct a lot of representations. Now, how I started off with these building blocks. So what are they? Now I can define them for you. So let me go once more back. So this is how to construct a lot of representations. But what are the representations that are missing? These are the building blocks. And that's the definition here. So from now on, I will drop the word smooth because I can't write smooth all the time. It's just getting too much, too long. So all representations are smooth. And an irreducible smooth representation, IB, is called supercuspidal, these ones that I'm really interested in. If the following happens, if it does not embed into a proper parabolic induction. So that means you cannot find a parabolic subgroup that is smaller than G, like one of the ones from the previous page, such that the representation embeds into this parabolic. Which means, in other words, these are the ones that we need to construct somehow different. And here's a nice fact that explains why I call them building blocks. If you take an arbitrary irreducible smooth representation of your P-adic group, then there exists a parabolic subgroup and a representation of the Levy M that is supercuspidal, such that your representation you started with embeds into this parabolic induction. Now you might be a bit confused because I said the supercuspidal ones are those that do not embed, but the difference is that here I allow equality. So every representation can be embedded into the parabolic induction of some parabolic subgroup of a supercuspidal representation, and the supercuspidal ones are the ones where I have to choose P to be equal to G, so the trivial parabolic induction where nothing happens.
Does smoothness matter here, or is this true for all irreducible representations, or is it irreducible representations or irreducible smooth representations?
Everything is smooth here. I don't even think about non-smooth representation. Things are getting crazy then. Yeah. From now on, everything is smooth. So that means the supercuspidal representation, they are really the building blocks. And they allow us now to understand all representations because everything else embeds in them. And that allows us to even do this at a categorical level. So I write by Web of G, the category of smooth representations. If you don't know what a category is, don't worry about that word, just ignore that word. What it really means is I just look at all the representations and I look at the morphisms between them. That's just what the word category means. And the statement of what Bernstein found out in the 80s, I think, was that you can decompose this category into blocks. They are called after him. They are called Bernstein blocks. And they are indexed by M and sigma. M is the Levy subgroup and sigma is supercuspidal of M. And so how do I know what to put in there? Well, take an arbitrary irreducible representation. You know it embeds into parabolic induction coming from an M and sigma. And then you just put it in the block with the M and sigma written down here. So I should say that M is a Levy subgroup and sigma is supercuspidal. There are also non-irreducible representation. What do you do with them? Well, you just take all these irreducible ones, put them in the blocks, and then you just take everything you can build out of them and put them in the same block. So for example, if you take a representation, irreducible representation that's in here, then you take also the direct sum of the representation with itself and the triple direct sum and so on, and put it in there. There's a little trigger here. This means that you need to consider things up to equivalence, because, for example, if you induce something from M or from a parabolic containing M and sigma, if you conjugate your parabolic subgroup by some element in the group and then induce, you get isomorphic representations. So this trigger means up to an equivalence relation. The equivalence relation is conjugation by elements and also unramified twist for those who have heard the word before. So these are characters that are trivial on all the compact cycles. And that's just a technical detail that we can ignore. So that's nice. So we now know a lot about the structure suddenly. We started out with, okay, there are some smooth representations. We have no idea how they look like. And now we know at least they fit into these blocks. There's a lot of structure. So I just moved up the Bernstein decomposition. And I want to give you an example to actually see what are these blocks. So let's take my favorite group for talks, SL2. And well, what are the possible Levy subgroups? Well, Levy subgroups mean these block triangular matrices. What block sizes can we have? Well, we can have 2 by 2 block, so that's just M equals G, or we can have a 1 by 1 block and 1 by 1 and 1 by 1 block. That means diagonal matrices. And since SL2, the determinant should be equal to 1, it means T inverse is really what we have. So let's just look at the two cases. Let's start with the case where M is equal to G. In that case, well, sigma is a supercuspidal representation of G. We need to induce up from G to G, which does nothing. So that means the only irreducible representation in there is really sigma. And then we need to build everything we can build out of sigma, and that's just the direct sum of sigma with itself. So it's just the direct sum of vector spaces, and the action is just the direct sum. You can also take 3 times sigma and add them 4 times. Infinitely many sigmas can be added to each other. And that's all that is there. So that's a nice fact that you can't have some non-trivial extensions. So it's really, these are all the objects in there. And then you can ask, what are the morphisms? So there's a nice lemma, a Schur's lemma, that says that the only morphism of sigma, from sigma to sigma itself, so the only vector space morphism that commutes with the action is actually the scalar multiplication. So the only morphism from sigma to itself is scalar multiplication, and then you can deduce the same for, not the same, you can deduce what it is for these sums as well. It then corresponds to matrices. So that's the first block. That's a rather easy block somehow. I mean, well, easy up to we don't know yet what sigma is. So that's still the tricky part. Here's another example. Here's the next example. We said we take the T. I didn't actually explain why I call it T. T stands for torus. I think we have seen this in previous talks, that there are weird different tori that float around here. It's the diagonal matrices. And I take the trivial representation. That's the nice supercuspidal representation because, well, the torus doesn't have any proper Levy subgroups, which means all the representations are supercuspidal because nothing comes from parabolic induction from something smaller because there is nothing small. And then it's a big question, what is this? So how do we find out what that is? Well, I said we need to take the parabolic induction from a parabolic containing T, that would be the Borel subgroup, these upper triangular matrices, of this trivial representation. And then it turns out that, nice exercise, you can actually work that out, that the trivial representation is contained in there. That's great, so we should take the trivial representation to be in this block. But it also turns out that there's a quotient. And this is called Steinberg representation. That's just the name for it. So that's the definition of it. And it turns out that actually this is a non-trivial extension. So the Steinberg representation is not a sub-representation of the parabolic induction. It's only a quotient. So this is not a direct sum of the two. So that means inside here we also have the Steinberg representation. We have the direct sum, but we also have this non-direct sum, this weird extension. Which just means it's complicated. This is called the principal block, and it's complicated. So let me give you the answer of what it is. It actually turns out that this is modules over something nice, something that's called an Hecke algebra. What is this? The main thing that you should take away is something explicit, and here's an explicit formula. It's an algebra with generators T sub W. Let me start with what W is. Small w is an element of the affine Weyl group, WF denoted, which is the group generated by two elements, 0 and S1, with the property that the squares of each element is 1. How can you think of this very explicitly? Well, you just take, so short, you just take the real line, take 0, take 1, take reflection across 0, take the reflection across 1. These reflections, they have order 2, indeed. And you take the group generated by these two. That's the group we look at. And then for each element in this group, we take T sub W a basis element. So as a vector space, this algebra is just the complex vector space with basis elements T sub W. And then the algebra means there's also multiplication on this vector space, and the multiplication is given by the following relations. If you see this the first time, don't be scared. Just accept there is something complicated. If you have seen this before, maybe you recognize it. If you haven't seen it before, maybe you go in the future to a talk and see it again and then recognize it. So the relations are, there's a length functions on these elements, and you have to distinguish the two cases. If the length of Si, your generated time W, is longer than the length of W, then it's what you would want to do. Then the product of TSI with TW is just T of SIW. That's somehow nice. The problem is if the lengths get shorter, then there's this weird relation. So then this product is P times the thing you really want, T sub Si times W. But then there's this extraneous thing, this P minus 1 times TW. So that's just what it is. Mathematicians are really excited about this. For some reason, mathematicians like this. That appears in quite a lot of different areas. So that's really what people study. So people actually understand that, like other mathematicians. And so that means they also understand these modules. All right, so that's, yeah.
Is there a reason the lengths can't be the same?
That's an excellent question. Is the reason the lengths cannot be the same? Yes, the lengths always gets you always add 1 or subtract 1. That's just a property of Coxeter groups. So the length means what is the minimal number of generated S0 and S1 such that you can write your W as a product of those. And then there are lemmas, I think called exchange lemma, deletion lemma, that tells you if the length is not longer, if there's a shorter expression, you can find it by deleting an even number of things. Even what, yeah, I think that's, well, you can make it shorter by deleting 2 things. That's the statement of that lemma. So that's why you know it's either longer or shorter. All right, so that's an example. And now the big question is, how do they look like in general? So that's our second problem. So remember, first problem was, what are these supercuspidal representations that index everything? And once we know what the supercuspidal representations are, the next question is, yeah, what are these blocks? How do they look like? Here's the vague answer. So the vague answer is, and when you see this the first time, you wonder, what is this good for? So the vague answer is, this thing is the same as the thing with zeros added everywhere. Awesome, isn't it? Let me explain a bit what this is. So the G0 is a subgroup of G. So far, so good. M0 is a levy of G0, and sigma 0 is a supercuspidal of M0. But so what is so nice about this is that the sigma 0 is what I call, and explain later, a depth 0 representation of M0. So here's the vague explanation. It means sigma 0 corresponds to a representation of a finite group, which means it corresponds to some of these representations that we encounter in Charlotte's talk. So Charlotte's talk basically has been about these, secretly about these depth 0 representations. That's where she might be going. And so that means while general blocks are very complicated, we reduced everything back to representations of finite groups. So you can forget about these weird P-adic groups and actually study finite groups, which is much easier. It's still very complicated. Mathematicians have worked on it for a long time, as we learned from Charlotte, but it's easier. And then the other nice thing is that actually we already know what it is. So these blocks corresponding to these zeros everywhere, so if this supercuspidal is of depth 0, we understand explicitly what it is, thanks to work of Morris in 1993. And well, I add, or should say, that's joint work with Jeff Adler, Manish Mishra, and Kazuma O'Hara. And it's a slight lie, it's not all due to Morris, we had to add something to it. But roughly already in the 90s, we knew about the structure, that this is equivalent as a category to modules over some Hecke algebra. So that means I've written now here formula, can essentially ignore it. Let me just say that's a semi-direct product of a group algebra. So that's just something rather easy, except there's a small two-course cycle in it, and an affine Hecke algebra, the style we have seen before. But these symbols aren't so important. More important is it's something with explicit generators and relations. It's something we really understand, something people have studied. So it's something explicit rather than this weird representations of P-adic groups that we don't know what they are. So that's the big answer. Why do we care? I said we need to say a bit about why do we care. Well, there are many applications to the representations of P-adic groups themselves. For example, in general, I expect we can reduce a lot of problems to representations of finite groups because suddenly everything is equivalent to representations of finite groups. So if you do it in a nice way, you can reduce a lot of problems to the setting of finite groups where answers are either known or much easier to find. There are also applications to an explicit local Langlands correspondence, which essentially you can reduce it to finding an explicit Langlands correspondence for depth zero representations, which again is easier and is work in progress. But both are work in progress, to reduce it to depth zero and to use the depth zero. But you can even go beyond and apply it to something that is fancy nowadays, which is a categorical local Langlands correspondence. Somehow people nowadays like to view everything at higher levels, higher categories all around. And so in particular, people try to upgrade the Langlands correspondence from something that is just take a representation, attach a Langlands parameter to some categories. You take the derived categories of representations and send it to some category of sheaves on some space. Something weird. But if you want to do this, now since we know that even as a category, even when we consider extensions and morphisms, all these blocks are equivalent to depth zero block, that means also the categorical local Langlands correspondence can be reduced to depth zero. And there is actually current work in progress. So Shinwen Zhu announced already last year that he can prove a categorical local Langlands correspondence in a depth zero case. So that was already there, or up to him actually writing and releasing the paper. And once this is done, then we can hopefully reduce everything to that case. All right, so that's the broad overview. Any questions on this?
If you have this Hecke algebra, and just in the case of the trivial character, and we want to write a representation, can you explicitly write a representation as a module over this algebra? Like you can explicitly write the algebra, but can you also explicitly write the representations as modules? Does this make sense?
Sorry, can you repeat this question?
Yeah, sorry. Your category representations, it's a category of modules over an explicit algebra.
Yes.
Can you write down the representations explicitly? I'm not sure exactly what I mean.
Do you want to,
like, if I give you the trivial representation, can you give me the module
yes.
that corresponds to?
So the correspondence between representations of P-adic groups and modules over Hecke algebra is very explicit.
Okay.
So you can go in both directions very explicitly. In one direction, you take appropriate fixed vectors. In the other direction, you tensor with appropriate things. So it's very explicit to go between these two worlds. Yeah. All right, so let me say a few things. We should always acknowledge what people have done before us. Somehow, people haven't done much before on this question, surprisingly. I mean, I said that since the 90s, we know what these depth zero things are. And we already knew that everything looked like it should somehow reduce to depth zero. But if you just look at general groups, I'm not looking at special examples. In special examples, people have worked out things like for classical groups and GLN or special examples. If you look at general groups, there are essentially only two results. In 1998, Roach looked at the one extreme case where this Levy subgroup is just diagonal matrices, so just a split torus. That's the one extreme case. And in that case, sigma is just a character, it's one-dimensional, so it's actually nice. And then recently, Kazuma O'Hara, who was a master student at that time, looked at the case where M is equal to G. So that's the other extreme. It's the case for SO2 that was rather boring because there we just had sigma, sigma plus sigma and so on. So in some sense, this looks rather boring. There are cases where it's a bit more interesting, but it's in some sense the easiest case. And so now you wonder what is in between. There's a lot in between, and well, it somehow took more than 20 years to figure out how things go. All right, so this is the end of the overview. Now I want to go back to problem one, tell you a bit what we know about problem one, and then tell you a bit how we can approach this. So I said problem one was we want to construct these supercuspidal representations. So what do we know? I want to draw a picture. Those who've seen me give talks before have seen this picture before. So maybe I should first say, so in the case of before I draw the picture, in the case of GLN, this has been known for 25 years or so, but now 30 years, time flies. Yeah, something more close, something in the 90s. Thanks to, well, people started trying to construct these things 50 years ago, or more than 50 years ago. And people first started with the group GLN, the n by n invertible matrices. That's a good starting point because you can write them down easily. And then Moy and Howe, they did a lot of work initially, a lot of people worked on it. And then Bush and Kutzko finished the story in the 90s to construct all the representations. Then people looked at classical groups. So these are these groups, the orthogonal symplectic groups, also the unitary groups. That's done maybe 15 years ago by John Stevens. And then inner forms of GLN, so that's GLM of a division algebra, that was done by Schaefer and Stevens around the same time. And what I'm really interested in is to do it for all groups together, and also these weird exceptional groups and everything. And so there, it took some time to get started. And in the 90s, Moy and Brasset, they introduced an important notion which they called depth. So what is the depth? I said we look at smooth representations, which means smooth means that every vector is fixed by some open subgroup. That's what I gave as definition. But so this open subgroup, it might be huge or it might be tiny. And so what Moy and Brasset did is they defined a filtration of our group by compact open subgroup that gets smaller and smaller and smaller and smaller, like these red circles I've drawn earlier. And then they said the depth is how far you have to go down in the filtration until you get fixed vectors. So it has high depth if you need to go down very far in this filtration. And depth 0 means it has fixed vector under the huge maximal complex, or something slightly smaller. And so what Moy and Brasset did then, they introduced this invariant that's very helpful to study representation, and then they studied these depth 0 representations. I draw in this direction a prime number because some results depend on what P is, the P of the P-adic field. And so Moy and Brasset studied all these depth 0 representations, and Morris did the same roughly around the same time using a different approach, using Hecke algebras. And then the question was, well, how do we go deeper? How do we find representation of positive depths? And in 1998, Jeff outlined his PhD thesis. If you're looking for PhD thesis, well, this one has been written already. He constructed some representations of positive depths. And then JKU looked at it and found out how to construct many more representations by generalizing this vastly. And so all these dots, they should represent some representations here. And I guess I put my initial there. That's a longer story. Short version is that recently people encountered that so JKU wrote on a construction and proved that these are supercuspidal representations. And his proof relied on some other result in the literature. And it turned out that in this other result, a ±1 was missing because somehow, I think it was at the time where you handwrote papers, gave it to the secretary who typed it for you. And somehow the ±1 dropped out. I don't know when and where it happened. The problem is if you put the ±1 back into the paper where it should be, it has to be there. The proof of JKU broke down. So that happens, I think this happened maybe 5 years ago or so, as some people noticed that, like long time after this was written. So people were a bit worried, and eventually we realized, okay, no problem. It still provides a supercuspidal representation, all is fine. I just needed to provide a different second half of the proof. The first half is fine, the second half needed to be changed. So that was a relief, so because a lot of people work with these representations, assuming they're supercuspidal. But well, that happens, but now it should be fine. And so then the question is, well, Aaron, it's nice to have some representation, but really what we want is we want all representations. If you want to make statements about all supercuspidals are nice, we want to know how to write down all of them. And so big breakthrough was obtained by a woman and Julie Kim around 7 years or so later, 6 years later. And Julie Kim showed that if we are in this region where the prime P is very, very large, and if we work with QP, this characteristic zero field, not the characteristic P field, actually we get everything from use construction. So if you want to prove something about an arbitrary supercuspidal representation, you now have something in your hands. You can use use construction, write down explicitly how these representations look like, and then prove something with them now that you know how they look like. So that was a big breakthrough back then. Then shortly, when was that? A few years ago. Math is not my strength. Well, that sounds odd. Around 10 years ago, Rita and you, together with Rita and you, gave some construction of some representations. They said, suppose there is a nice input, then they construct an output, which is some representation that are smallest positive depth, so they are close to the surface. They called the representation epipelagic representations. So that's an odd word, and Margarita explained this to me. So epipelagic comes from oceanography. The upper zone of the ocean, the zone that can be reached by sunlight, that's called the epipelagic zone. And so they constructed these representations that are very close to depth zero, that are smallest positive depth. And Margarita told me he thinks of representation as fish that swim in an ocean. So these are all fish in an ocean. And so the upper zone are these yellow epipelagic. And so they had this input, and when the input exists, they gave construction that's very easy and produced some nice output. I mean, in the sense it's easy to perform, not easy to come up with. It's often the case that things that look easy are difficult to come up with. And then partially in a joint paper with Beth Romano, I also did the general case, we produced more input for the construction that in particular results in representations for small primes that were not previously there. So that means there's something else, out here. Well, you might ask, well, but where is there more? Which region is the more? Which region do we get everything? And so it turns out there is a region here where there are a lot of blue dots, the region where P is just large, not very large. And it turns out we get everything just in this region where P is large. And moreover, this extraneous thing got removed here as well. We don't need to assume that we work with QP. We can also work with the sister field, the Laurent series over a finite field. So let me state this as a theorem. Suppose the prime P is large. What does it mean? Here's the answer what it means. It means that P doesn't divide the order of the while group. The while group is something attached to each group. Here's a table of names. If you have seen these names before, I talked about names for P-adic groups. The name for GLN is AN minus 1. So that means for GLN, the while group is actually just a symmetric group on n letters. It corresponds to permutation matrices. And the order of the symmetric group with n letters is n factorial. So we want for GLN that P is larger than n. And the same for these groups, the classical groups want P to be larger than n. So these are the names for these classical groups. But there are also these exceptional groups. And there we exclude in worst case the prime 2, 3, 5, and 7. Even though the order is huge, it's 2 to the 14 times whatever, we only exclude 4 primes. So it's actually not that large. And so under this assumption, use construction provides us with all the supercuspidal representation. That's something that I actually wrote while being at the IES. Thank you for hosting me. And the condition is also optimal in general. I put a little star there because I don't want to go into the details of what I actually mean, but essentially, we don't expect anyone to come tomorrow and say, oh, we proved use construction gives us everything, even for small p. That's already not possible because of the yellow dots here that I knew. And also I have a joint work in progress with my postdoc, David Schween, where we provide new supercuspidal representations that are arbitrarily deep. So not just those that can be reached by sunlight, but also those that are down deep in the dark ocean where we need, I don't know, flashlights to see them. So these are the green dots. So that's kind of work in progress. And my postdoc, David Schween, has been already giving some talks about it in the process of writing the paper. All right, so that's the state of the art. That's the answer to what I mean with, we know it how to construct supercuspidals in almost all cases under minor assumption. This is the minor assumption here, the P is large. All right, so I want to show you now how such a representation looks like, to just give you an example. Unless let me go back. Are there any questions at this? Yes.
Could you give an example of the depth filtration?
Could I give an example of the depth filtration? Yes. So, can people see here? Let's take SL2 over QP. There are essentially two interesting examples, and then you can tweak them a bit. So one example is, so as at depth 0, let's say, or you can't see, I guess, this. So at depth, here's the depth, at depth 0, we have just the matrices with ZP everywhere, so that's just the compact subgroup. And I need to write determinant equals 1 inside SL2. I might just drop that. I hope you can just think of that all the time. And then a subgroup, you can just take the congruence filtration subgroup. So you can like all the matrices that are of the shape 1 plus PZP on the diagonal, PZP off diagonal. That would be depth 1. You can take this, all the matrices that are 1 plus PZP, a P squared ZP on the diagonal, P squared ZP off diagonal, and that's depth 2, and you can keep going down. Just take all the matrices congruent to 1, the identity matrix modulo P to the n. That's one nice filtration, and that's something that is rather well known, I think, in general. People like to work with congruence filtration. And what Moya Prasad now observed is, actually, you don't need to have jumps everywhere. Like you don't have to go down on the diagonal and the off diagonal at the same time. So what they did is they started with a different group, and this is actually due to Brier and Tietz. They classified compact subgroups, and another nice compact subgroup is one where the off diagonal element here is slightly smaller. So we have the same group, except I put a P already here, so that's a bit smaller. And now the depth doesn't really work anymore. So let me put the depths here, 0, 1, 2. And now the fun thing is that at first the diagonal gets smaller, while the off diagonal stays the same. So that's a nice subgroup. And this first one has depth 0, the next one is at depth 1/2. We need to put something in the middle. And then we change the, sorry, did I say off diagonal? First we change the diagonal, and then the next step, we change the off diagonal. So in the next step, I'm increasing this P to P squared and add a P here. And that's then the depth 1. So in some sense, to go from here to here, I make everything smaller. And there's something in the middle where I first make the diagonal smaller and then the off diagonal. And you can guess the next step would be, again, it's the diagonal that needs to get smaller while the off diagonal stays the same. And then you can keep going.
How do the denominators in SL2 fit into the filtration?
How do the what?
The denominators.
What do you mean by
So
denominator?
this is SL2 ZP, but
Yeah.
you're giving, how does it depth 0 representation for SL2 QP? So these would be SL2 ZP representations.
No, this is just the Moya Prasad fit. You're asking for filtration.
Yes. I was asking for the filtration.
So these are just compact subgroups that then define the depth. So I just
Okay.
see where do I get fixed vectors, which of the compact subgroups give us as fixed vectors. Sorry that the laptop decided. Sleep. Yeah, and that's essentially up to conjugation and up to tweaking where the jumps happens, all the things you get for SL2. Okay, more questions?
Sorry, so just to make sure, these green dots are things that use construction doesn't get, so.
Exactly, the green dots are things that blue is U, JKU, and the green dots are those that he doesn't give us, and these are the ones that I construct as my postcard day between.
And is there no overlap, like your construction and your?
No, there is an overlap. The construction that we give recovers everything that JKU gives. We generalize JKU's construction. So what we do is we realize that actually the filtration that Moy and Passat defined is not enough. We define a finer filtration that gives us more representations.
What's the tool by which you know you have everybody?
What is the tool by which I know everything? So that's very different, and it's very interesting. Julie Kim had very abstract arguments using Plancherel formula, measures, blah, 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 something you need more complicated. What I do is I just create them. I mean, you give me a representation and I just give you the input for the construction. I mean, that's maybe not the tool, not exactly the tool. It's a bit more complicated. So what I do is I use the Brecht-Tietz building to find, like, basically the first step is if you give me a representation, I need to figure out what the depth is. So I look at all the filtration subgroups and see where do I get fixed vectors. That's the first step. And that's only a very small part of the construction of JKU. And then there's a much, maybe I shouldn't go into too much detail here, we can do this afterwards, but there's a, JKU has, in addition to the depth, he has a lot of more additional input data, and I try to recursively find the input for JKU's construction from the representation that you give me. That uses Brecht-Tietz theory, more Passat filtration, a fine analysis of the structure of these groups.
And is there any connection that you could point to Harishandra's work? The real case?
I can't. I mean,
Any?
supercuspidals don't really exist there. So Harishandra worked with real groups, and I said at the beginning there are these real Lie groups, and then there are P-adic groups. What is interesting is you learn in
The street series plays the same role.
yeah. So what's interesting, we learned in Charlotte's talk that there are these characters that, or no, we learned tomorrow. We learned today. What? Did you talk about characters?
Yes, today.
So we learned today about the characters of representations, and one can also define characters of P-adic groups. And it turns out that actually the character formulas, if you interpret things appropriately, are magically the same. But I don't understand where this magic is coming from yet. So that's Harishandra's Lefschetz principle, that there should be an analogy between the two things, but we don't understand yet why.
So just to be clear, the definition of depth is that when you get fixed vectors.
Exactly. Exactly. More precisely, it's the next, I mean, yes. Let's leave it there, exactly. So you see how far you have to go to find big fixed vectors, and that's there. All right, let's go through an example so that you actually see supercuspidal representations when you leave this room. So that you have seen them when you leave that room, not while leaving it. So here that's just a recall what ZP is. Power series QP is finally many negative exponents. And now we have, I start with the group G being SL2, and inside there I take a compact subgroup SL2 over ZP. And I want to start constructing a representation of this compact subgroup. So that means I want to give you a map from this group to the space of endomorphisms of a vector space. That's what a representation is. That's what I need to give to you. So how can we possibly do that? Well, here's something nice. We can quotient out the next filtration subgroup that's conveniently already written here. So we just quotient out by that subgroup. And so one nice thing is these are actually all normal subgroups inside each other. So this quotient makes really a lot of sense. We get a group. If you do this, you can try to do the exercise. You end up with matrices over the finite field of determinant 1, essentially because the difference between ZP and PZP is just this zeroth quotient. It's just this A0 here, which is a number between 0 and P minus 1. So for each of these entries, the difference is something in a finite field. And now it's much easier. Now we have a finite group. So we are back to Charlotte's talk, and we can construct representations of finite groups. So that's just SL2 over finite field. So in particular, in general, it's a finite group of Lie type. And I just take an irreducible cuspidal representation of that. What does cuspidal mean? As before, it means it doesn't arise from a parabolic induction. What does this more concretely mean? In Charlie Chan's talk, you actually wrote down all the possible representations of SL2, or at least counted them in some way. And the cuspidal representations are those of dimension p-1 or p-1/2 that you saw in her talk. So it's something very explicit. You can look at your notes, can actually work that out. More precisely, in the setting, cuspidal actually means that there is no vector in your representation that's fixed under upper triangular matrices with ones on the diagonal. So you can look at the representation and just check that. So it's something.
We proved that today.
Yeah. You proved it today.
In the notes that I gave you.
Excellent. I did, yeah, I should have come to your class rather than in your notes. Perfect, excellent. So you already know this, so great. So here's something you know, and now we get something new that you didn't know before. So now we have a representation of a compact group, and now we want to build a representation of G. So we know we do the thing that we love to do is we induce. And what do I take here? I take something where I put a small c here, that means compact induction. It maps from G to this vector space that satisfies the standard relation. This time I take my K inside this capital K, this compact group. And compact induction now means that I ask my function to be compactly supported. It's done automatically locally. And the action is again just this right translation. And that's an F0 representation. Ta-da! Here is a supercuspidal representation. So it's not trivial, you have to prove that. That requires some work, but here is a supercuspidal representation. So now we have seen one. What are all the other F0 representations? It's always the same idea that we start with a maximal compact subgroup here, a particularly nice one, and then we quotient out what's called the pro-P unipotent radical, a huge normal subgroup, and then the quotient is a finite group of Lie type, and then you take an irreducible cuspidal representation of that, and then you compactly induce. These are the F0 supercuspidal representation. And for generality, if you replace SL2 by general G and K by general nice maximal compact subgroups. And then you learn from Charlotte's talk how to do that. I guess you looked at the case SL2, but you can do this for general. So these are the F0 representation to which we reduce everything. All right, let me move the example down and let me tell you how to get everything else. Here is a fault-block conjecture that's a theory in many cases. So all the supercuspidal representation that we constructed so far, like all this picture that I've shown you is all the dots, they are all constructed in the same way. They are all constructed via this compact induction. So these are all functions where we take a compact mod center, open subgroup in G. This mod center is just if there's a center, we need to include it. Just ignore that. And then take some representation of K that is finite dimensional. So here we are back to the finite dimensional world, much nicer than infinite dimensional world. And then we just compactly induce. So we take all these functions that transform via this representation on K on the left and that are compactly supported must. It's a fault-block conjecture that everything arises in this way. We don't know yet, but everything we know, all the representation we know are of this. All right, so the last part is now, so this is now the end of the supercuspidal story. The last part is that I want to give you a bit of a hint of how do we understand these Bernstein blocks. So that's what I said was the second problem. Are there any questions about this first problem? Yes.
Yeah, I have a question. So could you use this to actually construct, let's say, like a depth one representation, kind of like recursively?
Can you use that to describe a depth one representation? Excellent question. No, you can't, because unfortunately or fortunately, if you do this construction, you always have a fixed vector under this group. So this group here acts trivially, which means you have something just below depth, just this first group that matters, the zeros group. So that's always a depth zero representation. When you want to construct depth one representations, you will have to take something that is trivial on just the piece below one. So it has to be trivial on here, but non-trivial at the depth one piece.
Right.
And that's more complicated to construct.
So basically what you're saying is like, and now literally replace this CP, like this second part just from the depth zero to literally with the depth one block part and then modding on the depth two part.
Exactly, that's what you can do. It will be more complicated than the depth one part in general. It will be a complicated group that contains this one, is somehow built out of some depth zero piece of another group and that group. And so that's a bit more complicated, but in general, the rough idea is you take always a depth zero piece of some subgroup, And then you take smaller groups for the rest of it, and there essentially you just have a character. So you combine having a character of higher depths together with the depth zero representation in general. The construction is then more complicated, which is why I'm not talking about it here. I've recently written expository notes for an IHES summer school that are on my website. If anyone is interested in seeing more details, that's a good source. More questions at this point? So then we dive into the last part, which is to understand the problem 2. How do we understand these Bernstein blocks? So let P be large to simplify my life. So now the claim is, that's based on work of JKU and Julie Kim. They constructed these things, and together with my exhaustion proof, it says the following. So for all these Bernstein blocks, take one of the blocks you want, so choose M and sigma essentially. There also exists a nice compact subgroup and a representation of it. But so what can't happen is that, well, this is not the compact induction anymore, but somehow the compact induction encodes the block. And here's the answer of how it does it. The answer is that such that for every irreducible representation pi v, the following holds. This pi v is inside this Bernstein block, if and only if it is a quotient of the compact induction. So the compact induction is no longer an irreducible representation, it's not supercuspidal, but it encodes all the representations by just looking what's in the quotient. Another way to phrase this is, that's called Frobenius reciprocity, is to say that it's really difficult to check if something is a quotient of a compact induction because this compact induction is huge. Much easier is to check the following. You take your representation, restrict it to the compact subgroup K, and then check if it contains your finite representation V rho. So really, what does it tell you? It tells you if you want to know if something is contained in this block, you just take your representation, restrict it to a compact subgroup. There it's nice and easy, and you can see, does it contain the finite dimensional representation or not? And here's the corollary of that result. So the corollary is, well, that's work of Bushnell and Kutzke, and that stated that if you have a K in the row that satisfies this property, then you know that this block is equivalent to modules over Hecke. And again, this equivalence is, as I was asked earlier, something you can write down very explicitly. So in some sense, it's just you take an appropriate isotopic component. So an appropriate subspace where K acts by a rho. And what is this weird thing? So this is something we understand rather well. And here's the official definition. So this is what I call the Hecke algebra. And here's the definition that should now look similar to what you have seen about the induction. Now it's mapped from G not to the vector space, but to the endomorphisms of this vector space, just as a complex vector space. So just n by n matrices if this is n-dimensional. Which now has the property that f of k1, g, k2, where k1 and k2 are inside my compact subgroup and g is in my group G, satisfies the property that on both sides they pull out via rows. So we have this formula where f of g is an endomorphism of the vector space. It's n by n matrices if this is dimension n. And rho is, these are also endomorphism of this vector space because that's what rho of an element in K is. It's an endomorphism of the vector space. So these are just 3 n by n matrices that we can multiply. So that's what that formula is. So the difference from before is before we had here a vector and here an endomorphism. Now all of these are endomorphisms and they pull out on both sides. And that's something very explicit. Again, you can write this down. It's an algebra. You can write down a multiplication on there. It's just some integral called convolution. And that's what it is. So that means we now have a way to find out what this is. Why are these structures of this Hecke algebra? And here's the result of Morris that I alluded to earlier, and also work in progress to actually get this exactly on the nose, which says that if this m sigma here, the sigma is a depth zero, if the sigma is a depth zero representation of m, then we understand how the Hecke algebra looks like. It's a semi-direct product of two things, this affine Hecke algebra, like these things that have generators indexed by affine Weyl groups and these weird relations, and the group algebra that's twisted. So that's what we knew already in the 90s. And what I'm going to do now is I combine these theorems in one. So let's actually see what do the theorems say. the theorems say that there exists this compact subgroup in the representation rho such that we have this equivalence here. So that's what I've now combined up there, is that there always exists this K in rho such that we have. And so Morris now said we understand the Hecke algebra in the depth zero case. And here's the theorem in progress that I'm working on with my collaborators. We show that for every m sigma, so now I'm trying to make the statement I said before precise. For every m sigma, there exists a depth zero pair, so an m0, which is a Levy subgroup of some subgroup G0 and a depth zero representation sigma 0 of it. And for this pair, for G0 containing M0, the Levy, and sigma 0, there exists also a compact open subgroup K0 and rho 0, like the one above K and for K and rho for G, such that we have an isomorphism of Hecke algebra. So we produce an isomorphism of the Hecke algebras on the nose of these Hecke algebras that I've shown you on the previous page. The proof is complicated. The proof relies in particular on some technical result that I've proved with Tasha Kaleta and Lauren Spice recently, which, let me just say a few words about this. So I said this proof of JKU unfortunately broke down because the ±1 was missing. And so a lot of things in the literature always needed to be corrected by ±1. And so what our idea was to put ±1 back into the equation, to twist everything by ±1 so that it disappears everywhere and that everything looks much cleaner. And that's what we did. It sounds easier than it was. And that's a key ingredient. Without that, it doesn't work. And so in particular, a corollary of that is now that we get an equivalence of the Bernstein blocks, because the Bernstein blocks are just modules over these sections. Okay, let me just say one more anecdote at the end. So I've started giving talks about this result recently, and then after the talks, people often came to me and said, I don't believe your result. And so, not really what you want to hear after you give the talk. And so, well, there were several concerns people had. So one concern was people said, oh, that's way too easy. These complicated Hecke algebras, they can't look as easy as this. But I don't know what to tell them. Like, it is the case. I mean, I've proved it, or we have proved it. So this concern, I can't really do anything other than tell them, well, that's what it is. The other concern is much more helpful. People came to me and said, here's a counterexample. And so that happened more than once, but we studied all the counterexamples, and none of the counterexamples was actually a counterexample. All the counterexamples were just missing this twist. If you don't put in the twist, you can find tons of counterexamples. This doesn't work. You really need to include this twist by a ±1. And so maybe that's also why it took so long to actually get this result. So mathematicians for more than 20 years were actually thinking that should hold. Well, then some people said it shouldn't hold. There are counterexamples. So there was actually, it wasn't clear if it's true or not. So it also requires courage to just keep going and believe in things. Let me just finish by an overview of what we have done. So we have studied representations of P-adic groups. We saw that we know the building blocks in almost all cases, and we now understand that category decomposes in blocks. Each block is equivalent to a depth zero block, and they are equivalent to nice modules of a Hecke algebra. Let me stop here and ask for more questions.
Question?
Yeah, let's start with you. Okay. Is there a way one could think about why a Levy subgroup and a supercuspidal is associated to a compact subgroup of G? Is there a way to like sort of understand it?
I don't know. It's a good question. So the question is, I don't have a good answer. I need to think a bit more about it. And the whole theory is called type theory. These K rows are types, but is there a good reason to believe they exist? I don't know, other than, well, I know how to prove it. Yes.
You can feel free to say, tell me the answer later, but if you take G to be GL2 and M to be GL2, and you take a positive depth supercuspidal, Can you tell us easily what like the G0 and the M0 and the sigma 0 are?
So I take G equals M, I take a supercuspidal of positive depth. If you assume that it's honest positive depth, so that it's not just twisted by a positive depth character, then the G0 will be an anisotropic torus. So, if I haven't heard these words before, it might look like something like A, B, like matrices of that shape, and that over, well, that's one example. Instead of P, you could also use something else there, something that becomes isomorphic to diagonal matrices over field extension. In this case, once you adjoin the square root of P. And yeah, so that would be your G0 in that case.
I don't know how like related this is, but there was like a slide a while ago where you had like this, I think it was like the first slide you started talking about like algebras where you had like the reference relation on the P's.
Oh, yeah.
You mentioned that like this is like a lot of people care about this. Could you say a little bit more about that?
Yes, I'm not sure I'm getting.
That
Yes. Well, in general, there's a whole story about Hecke algebras where you take more general affine Weyl groups. So these are groups that are generated by appropriate reflections. And then you have similar relations for all the, the relations look like that. It just shows up in a lot of areas of mathematics. Somehow it's people who study algebras, they like these Hecke algebras, they try to study what the representations are. It's somehow something that has a nice structure and that pops up naturally in various different situations. I'm not sure what was exactly the question, why mathematicians care?
or like it pops up in my research, so.
Oh, it pops up in your research.
I just wanted to know like what
Excellent.
other areas it pops up in.
Well, in yours, for example. We can try to brainstorm afterwards a bit more together. I meet regularly people who say they care about it. Now I just met another one, which is excellent.
I have a question about this slide, actually. Thank you for asking this question. The equivalence class, you said it's about twisted with a ramified character. Yes. So should I think that all the twists of the trivial are in the same, like, yeah, yes, but then they don't have extensions, or do they have extensions?
I'm not able to answer questions about extensions on this
Okay.
one, but you're right. So everything that if you take a non-ramified character here and induce, that will be also contained in that block.
Thank you.
Well, so there must be somehow extensions, otherwise it wouldn't be in that block. I mean, these are really the blocks, so these are the minimal blocks. You can't divide them any further up.
Okay.
So there must be somehow some extensions. Yeah. So these are really the smallest possible blocks, which in other words is the definition of block.
One more question. Let's thank Jessica again.